So this is the first in several parts looking at resistance, electrical resistance. Usually they have a symbol, something like that. It's meant to be a rectangle, and R is the symbol. And the units for resistance are ohms, symbol omega. Okay, ohms. And to give a bit of background to this, first you need to understand conductors versus insulators. I've talked about this in other videos, but mentioned again here. In any conducting material you have atoms, and those atoms will have electrons orbiting around them. And in the conducting material, those electrons are free. That is, they're not used for bonding or anything, they're free to move, free to drift is the word. They actually talk about a drift velocity of the electrons, but they can travel from one to the other. The charge, the positive charge in the nucleus is not preventing the outer electrons from jumping around and moving anyway. And we've seen before in earlier videos in electricity that if you put an EMF, so you have positive and a negative, whether it's from a battery, some other power supply, the electric field's generated between there, with the direction being that of a positive charge, which means any electrons are going to go towards the positive side, and overall they start drifting in that direction. I think I mentioned there are several different velocities of electrons. You can talk about their random drift velocity, you can talk about so it's their drift velocity, their overall velocity moving that way, and you can talk about the velocity of the energy transfer, which is something different altogether, and that's the fastest one, because as soon as you connect a battery it you get energy transferred, and it's obviously not the electrons that are coming out of the battery that are going all the way around. There are electrons sitting in the conducting material that are waiting right there. So I was just interrupted, but carrying on. So understanding conductors and how they conduct is really important. Insulators, the short of it is that the electrons are busy bonding to make the structure a rigid crystalline structure, such as in silicon, and so the electrons are not free to conduct. Now, so that's the general background. This next point doesn't take too much, but basically resistors are conductors of a bit more higher resistivity, if you like. They oppose, let's just get another colour going on here, they will oppose the flow of electricity, or so oppose electron movement, we'll put it that way. Electron movement, they oppose that movement just a little bit more, and a bit more, that's the key. So a bit more than the average other conductors. Okay, so what that means is you might have copper wire in your circuit, and then all of a sudden you've got resistance wire. This is the old symbol for resistance, and that resistance wire might be made of something different. So usually, let's see, nichrome wire. And the reason nichrome wire is resistance wire when the copper is not, is that the copper doesn't hold on to its electrons quite so tightly. But the nichrome wire, it likes to hold its electrons a lot more. So that's really important. So anything with higher resistance, it holds on to electrons more, in particular than copper or something like that. So yeah, resistors are, I've lost my, you've probably got it, but I've lost my little bit here. There it goes, the list of what's happening. So resistors are conductors. They're just conductors that hold on to the electrons a little bit more. Now we need to look at factors that affect resistance. You can make a formula out of this, but keeping it really simple, resistance is affected by, let's change that to proportional, to the length. So if you make a resistor longer, you are requiring twice the amount of energy to go through. So it might take a certain amount of energy to go through one length of resistance. If you make it go through two, you have to use twice the energy. So changing the length, increasing the length, will increase the resistance. Okay, what else have we got? If you look at the, if you consider a resistor as a kind of a 3D, that's the end, and if we look at the cross section, so that we make it more paths for it to go down, so instead of just having one, we stick another beside it. Okay, I haven't practiced my 3D drawings for a while, but so now we've got two paths of resistance wire. This is not making it twice the resistance, this is making it half the resistance. So half the resistance. So what we can say, I'll just state it and then we'll explain in a bit more detail, that resistance is inversely proportional to the cross-sectional area. Okay, that is the cross-sectional area. So we've gone to times two paths of resistance, so it makes 2A, twice the cross-sectional area, making it half, when we put it into that 1 over that inverse formula, making it half as hard for it to go through. Now, I think of it like this: if you have students in a corridor, so here's your corridor, and you have students passing through the corridor. If you add another corridor side by side, you can get twice as many students to fit into that and passing through. So that's what's happening when you are decreasing the resistance by increasing the cross-sectional area. I also think if you were to add on more length of corridor, it's going to take twice as much energy for those students to pass through, because they have to batter their way through all the other students and lockers and different things that appear in corridors, and it can be an exhausting experience. But if you double the length, they have to use twice the energy. Okay, so that's your general intro to resistance. Next video looks at resistance in series and parallel and a few formulas.